Alright, now we're going to start looking at partial differential equations, and in particular linear partial differential equations. So in this video I'm going to give a brief overview on what we're going to be looking at. So if we can recap, ODEs dealt with conditions of one variable, correct? Let me make that look nice. ODEs dealt with conditions of one variable. So for example, we'd have something like y of x equals yada yada, right? But now for PDEs, this is where everything changes. In typical, for PDEs, we write our solutions with a u. So like u, at least my notation. And then in PDEs, typically the equations will now deal with time on top of x. So now we're looking at the change in whatever over x and time, which adds a whole another factor to these problems, as you can see. Now for this would be like a 1D case. If we have something like this with x, y, and t, that's 2D. If we have something like this, we're gonna have x, y, z, t, that is 3D. So an example of a PDE, let's look at the heat equation. So the heat equation looks like this. Alpha squared, which is just the constant of thermal diffusivity. I hope I said that right. So that's u squared times second partial derivative of x with respect to time is equal to time with respect to x. So this is the heat equation. And the heat equation governs the heat diffusion throughout an object. And in particular, we're going to be looking at metallic rods in this series because they're easy to model. So, for example, let's look at a metallic rod. Say you picture a rod, and say you heat up an end of the rod, or both ends of the rod, or the center of the rod. Doesn't matter. Just picture you're heating up the rod somewhere, and the heat is going to diffuse throughout the rod over time. So, what our goal would be to do is we want to find from this, given the conditions that we put into it, like say we heated it at the ends, right? That's a boundary condition. But also say we also might have an initial condition as well. But we want, with those, we want to solve for some u of x of t, which will give us the heat diffusion at some location on the rod x at some time t. So you see how powerful this could be. A lot of information in that one equation. So you can imagine this is going to be pretty difficult to solve, and partial differential equations are considered the final boss of mathematics, at least for engineers. So now, we're looking at linear partial differential equations, right? So like, for example, we see this heat equation here. This equation could actually be, before I get into that, let me show you a different form of notation that would make our lives easier. So typically what I do is I write my, so this, for example, would be u of x, right? This, for example, would be u of t. And that's just a different notation that makes writing equations a lot easier. So if we were to rewrite the heat equation using this notation, it would look like this. U xx is equal to u of t, right? So basically, after my description of the heat equation, we can say that PDEs, that solving a PDEs involve turning a situation, that's what we can call it, I guess. How do you spell situation? Situation that deals with multiple variables into an equation that models the situation. So you can see the heat equation starts out with partial derivatives, so it's a partial differential equation. What we want to do is we want to convert it into ODEs, and then we want to solve for an analytical solution. So let me go through a quick little outline of how to solve ODEs. I'll put it down here. We call it a quick outline. We're going to, of course, get more into detail of this stuff in my later videos. Quick outline of solution for solving PDEs, in particular linear PDEs. So the first step to solving one would be called separation of variables. Now this basically turns a PDE into multiple ODEs. Okay, so for example, if we have like a 1D PDE, that would result in two ODEs, typically. A 2D PDE would result in two ODEs as well, typically, as you will see later on. And a 3D, which I don't believe we will be looking at, but that'll produce three ODEs, and this is where it gets really complicated to solve. And that would be a very long video to make, which I don't believe we're doing that. We might separate the variables of a 3D PDE, but we're not going to go any further than that. So like for example, for the heat equation, we would end up with a second order linear homogeneous ODE, right, and a first order linear ODE. So I might as well write that down. Let's look at this. Let's look at the heat equation, because it does kind of become specific to the equation. So like the result for the heat equation would be second order linear homogeneous ODE, and of course I will show all this in the next few videos. And actually no, not for a while actually. And a first order linear ODE. And then once we get those ODEs, we go to step 2, which is called a boundary value problem. Now sometimes people or textbooks will kind of group step 1 and 2 together, I believe, or the next few steps together. I like to separate it out more because it makes a lot more sense. But basically what the boundary value problem does is we're going to use the second order. For the heat equation, we're going to use a second order linear ODE, the homogeneous ODE, to solve for our result. So what the boundary, so like in the case of the heat equation, we're looking at a rod, and say like for example we want to keep the ends of the rod at a constant 0 temperature. Well, those would be our boundary conditions, right? So like what we do with this is we're going to use our boundary conditions. And what this does is what I will show you later on, but we will end up with all right, hold on. Let me write down this. Solve the second order homogeneous ODE. We worry about the other ODE later on, but as a result, we end up with eigenvalues eigenvalue or eigenvalues, and corresponding eigenfunctions. Well, eigenfunctions. Okay. That's a boundary value problem, so BVP. BVP. So then after that step, we get our eigenvalues and corresponding eigenfunctions. Of course, this will make sense later on. We solve the first order linear ODE for so basically if the heat equation, we're dealing with x and we're dealing with t, right? So like for example, so if with the heat equation, what we would be doing with the second order homogeneous ODE and the boundary value problem, step 2, we would be solving for x, basically a function of a solution of x, basically. And then we solve the first order linear ODE for the other solution of t, and we do that by using, for other solution, I'll call it, for now. This will all make more sense later. Don't worry. We're going to do this by using the eigenvalue. Now, I make this a step. We basically put steps 2 and 3 together. And we get our fundamental set of solutions and our general solution. Well, we define a fundamental set of solutions, which allows us to get a general solution, basically. Which, for a heat equation, would be x of t, right? But now this would be in terms of a summation. And we're going to have a series. So, if we're going down to step 5, we're going to use the initial conditions for a rod and the general solution, which is a series, to solve a Fourier series. Which is typically a sine or cosine Fourier series. And actually the general solution here, I can write it right here, tells us whether we have a sine or cosine Fourier series And what step 5 does when we solve the Fourier series is what we do is we find, basically we write out the general solution, right? But then we're going to have what's known as Fourier coefficients or Fourier series coefficients. So we want to find, and of course this will all make more sense later, we want to find the Fourier series coefficients. And then we plug these coefficients back into the general solution. We write it this way: plug back into general solution. And then that gives us, by the way, the general solution is in the form of u of x of t, right? And that gives us our u of x of t that I first talked about, which is the function that describes the situation. Now, before I go into why you'd want to do all of this, I completely forgot to bring up linearity, or let me call it linear versus nonlinear. What makes a PDE linear or nonlinear? So basically, I'll ignore the definition of linearity for now, and we're just gonna look at as examples of how you can tell when an equation is linear or nonlinear. So for example, we know the heat equation is nonlinear, right? I mean linear, sorry. But basically, a PDE is linear if u and its derivatives only appear to the first power. So for example, linear if terms include, for example, u du dt, du squared dt, and so on. Non-linear if terms include one example would be something like this: u du dt, u du dt, second derivative. Oh crap. My notation's a little bit messed up here. Okay. Something like that. Or if we have something like u squared, or u, anything to the higher power, right? Anything like this to the higher power. That's all nonlinear. And for example, I don't know if you take fluid dynamics, you'll notice that the big beautiful maybe scary Navier-Stokes equation, that's a nonlinear PDE, because we have a lot of terms like this right here that are nonlinear. And as you know, those equations are very difficult to solve, and we really don't know how to solve them analytically. We have some self-similarity principles that we can use to find solutions of specific cases, and we can find exact solutions that simplify, because the equations simplify down a lot sometimes, but we really don't know how to solve the equations without making assumptions or making approximations. So that's why we're dealing with linear equations for now. Well, that's not for now, that's what we are doing. So, but why do you want to learn PDEs? For example, I just talked about fluid mechanics. If you want to understand fluid mechanics, you have to use Navier-Stokes equation to model turbulence, yada yada. The heat equation, of course, to model heat flow through anything. Say you're working on spacecraft and you're designing a heat shield, you want to be able to model the heat diffusion throughout the heat shield and whatnot. If you want to look at vibrations with anything, like structures, you could be looking at beams with vibrations. You'll actually need the wave equation for that. They use that a lot in quantum physics, I believe. So there's just a lot of applications. I mean, I think even finance uses PDEs. I'm not sure though, but I believe even finance uses PDEs. But of course, solving PDEs is not an easy task, I will say. There's a lot going on to solve a PDE. Each problem could take a very long time to solve, and there's a lot of steps, especially when you get the Fourier series. Typically pretty difficult to solve sometimes. But that's why I'm here. I'm going to teach you all the tricks and techniques to find the exact analytical solutions of PDEs. Now, really quick, I just want to go over a few types of PDEs. And we're going to go over this more at the very end of the series. We typically classify PDEs by their order, like their highest derivative involved, and like their behavior, which falls into three main categories. So the three main categories are called elliptic, parabolic, and hyperbolic PDEs. So we have elliptic. An elliptic, basically, I'm not going to write this out, but basically, because I'm going to go over this in the very, very end of the video. After I go through everything, I'm going to go into classification. But I'm just going to do a quick overview. We have elliptic PDEs, which basically, again, it's like Laplace's equation, where it describes like steady state systems, like that things, like systems that don't involve time, basically. Parabolic PDEs. That would be like the heat equation, right? Which models like diffusion processes, like how things spread out over time. And then we also have hyperbolic PDEs, which are more complex. Hyperbolic PDEs. And that would be like the wave equation that we're going to look at. Let me write that down. This is the heat equation. Elliptic is the Laplace's equation. That's actually also called the potential equation. And then the hyperbolic PDEs would be the wave equation, for example. And these describe like wave-like phenomena. Hyperbolic PDEs involve both space and time. And they have like a propagating nature to them. And of course, each type of PDE behaves differently. So you need different tools to solve them. That's why we have analytical methods. And as you'll see later on, elliptic PDEs, like Laplace's equation, typically involve not drastically, but different methods than parabolic and hyperbolic to solve. Parabolic and hyperbolic are pretty similar, but I will say hyperbolic and then elliptic are more difficult to solve than parabolic PDEs. You'll see why later on. So what's coming in the series? So what am I going to go over, for example? What am I planning to go over? Because it can always change, of course. Well, first, before we get into solving any PDEs, we have to learn all the steps. And I like to do that separately. So like, for example, we're first going to look at separation of variables. Separation of variables, and then we're going to do a bunch of examples of separation of variables. Pretty complex examples, actually, I have lined up. And then we're going to look at Separation of variables isn't too bad though. It's pretty straightforward. And then we're going to look at boundary value problems. I'll do an overview and then a bunch of examples, just like separation of variables. That's where it starts to get a little bit more involved, a little bit harder. So let me write that down. Boundary value problems. And then we're going to look at Fourier series. So I already have a video out deriving the Fourier series coefficients. I made that a little while back. So you can check that out. We're going to look at a little intro, but that's not necessary to solving them though, but I just have that out there. But Fourier series is definitely the hardest part of solving a PDE. Deals with a lot of integration. But then after we get this is basically everything that we need to solve PDEs. And then we're going to go into solving different types of PDEs. So now we're going to look at solving PDEs. Now I have a whole bunch of different kinds that we're going to solve here. So we're going to have heat problems, which are metallic rods. We're going to look at 0-degree ends. We're going to look at steady state solution. We're mostly going to look at the heat equation. We're going to look at non-zero. Boundary conditions, non-zero boundary conditions. Then we're also going to look at insulated ends. All this really does is change up the boundary conditions. Each one of these are just describing different conditions, different boundary conditions, but the method for solving them can differ for each one of them. Especially for the steady state solution. Steady state solution can pose its own challenges for the heat problem. After we get the heat problem, we're going to look at the wave equation. And with that one, we're just going to look at a string and different scenarios where we might have like an initial equilibrium position where the string is, say initial velocity, whatever. That's how those boundary conditions will work. But after the wave equation, then we're going to look at the Laplace equation or the potential equation. So we're going to look at our potential. Potential is a bit different. It's not really a physical kind of thing to look at, not like a rod or a string. It's more like a process. Like it's a potential. Like it could be like an electric potential, right, over an object. So like, for example, we can look at, what we're going to look at is we're going to look at a rectangle or a square and rectangle. We're going to look at both. Square is obviously easier than a rectangle. I can't remember what the difference is between the two. I know we're going to look at both though. And then we're also going to look at a circle. And that's the end of that. Those are the ends of those. And then I want to get into, possibly for the wave equation, I want to see if I can make a video on called the Amblerts, which is a famous name in fluid dynamics. We might look at the Amblerts solution to the wave equation, which makes solving it much easier, I suppose. But we might look at that, and then we might also, what we are going to do, we're going to do classification of PDEs after we go through all this solving. classification of PDEs, which will deal with, we're given a PDE and then we want to figure out how to find out if it's hyperbolic, elliptic, or parabolic, right? There is a way to actually figure that out without just having to look at it and be like, oh yeah, that's that. There's an actual solution to do that. It's pretty simple, actually. We're going to do that, and then we may look at the method of characteristics. Which is just another way of solving PDEs. Alright, well that's it for this video. Next video we're going to look at separation of variables. I'll do an overview and then we'll go into a bunch of examples. But I will see you in the next video.